Well, good evening, everyone. I'm Brian Hoskins, the Director of the Grantham Institute, and it's my pleasure to welcome you here this evening to our 2012 Grantham Annual Lecture. So I should give you a few words about the Grantham Institute for Climate Change. We were founded about 6 years ago with a generous donation from Jeremy and Hanny Grantham and through the Grantham Foundation for the Environment. And the aims of the Grantham Institute for Climate Change are to enable and encourage all the great climate-related research which goes on at Imperial, and then, based on that research, then to influence what goes on in the world. And that could be the world of government, of business, or the wider world of the people. So it's a great pleasure here to welcome Dr. John Holdren tonight. We were extremely pleased that he accepted our invitation in amongst the many invitations he must receive and the very busy agenda I'm sure he has. And so John did his degrees in areas associated with fluid mechanics and plasma physics at MIT and Stanford, and then he stayed on in faculty positions at Stanford for 20 years or more, and he then moved to Harvard and a number of professorships there, including a professorship in environmental policy, and in 2005 he became the director of the Woods Hole Institute. So he's had many awards, and he is a foreign member of the Royal Society, as well as being a member of the National Academy of Sciences and the National Academy of Engineering. As well as the great career in academia, he's also dealt with the big issues of science that are important to the world. And in particular, he was chair of the Pugwash Conference for many years, and their aim is to reduce the threat to humanity posed by nuclear weapons. And in fact, he was chair at the time they were awarded a Nobel Prize and presented the Nobel Prize lecture. He has also been outspoken on global environmental issues, and in particular climate change. And I could give you various quotes from some of his lectures in the past. Maybe that's not very fair, seeing he's taken on a political role since then, and perhaps I shouldn't throw those back in his face, but maybe at question time afterwards you can. So it's not surprising with his background that his government, and in particular his presidents, have asked him for his advice. And Bill Clinton then asked him to be a scientific advisor, and he was that. And then when Barack Obama became president, he also asked him to be the assistant to the president for science and technology and the director of the White House Office of Science and Technology Policy. So these are the offices that he holds now. And in fact, he was meant to fly here yesterday, but got a late call that he should meet with his president at 4:30 yesterday, and met with him for an hour. So we're very lucky that he didn't have to juggle between meeting his president and coming here for the lecture. He actually tells me that his president is so understanding that if there'd been a conflict today, he would have come here. So that's fair, very good. So, Dr. Holdren, it's a pleasure to ask you to present the 2012 Grantham Annual Lecture, Coping with Climate Change.
Well, thank you, Professor Hoskins, for that generous and, may I also say, somewhat provocative introduction, inviting embarrassing questions from the audience, but we'll see what we get. It is a particular pleasure to be here to give the Grantham Lecture, not only because it's a great pleasure to be back in the UK and to see again so many of my friends and colleagues from the science and technology communities in this country, but it's also a particular pleasure because I'm well acquainted personally with Jeremy Grantham, who, in addition to being a patron, as it were, of the Grantham Institute, was also a patron of the Woods Hole Research Center, which I had the pleasure to direct. And very interesting person indeed, and a generous donor to many important science and environment activities. I'm going to try to cover a lot of ground tonight. I'm going to do it with the benefit of a wordy PowerPoint. I'm not going to read you every word on the PowerPoint, but the benefit of the wordy PowerPoint, since I never actually prepare a text, is that there are enough words on the PowerPoint for it to stand alone as a record of the lecture, and I'm happy to make it available to anybody who wants it. So I'm really going to talk about three things. One is climate change science, one is climate change policy, and one is climate change communication. The overarching questions that arise under climate change science, I like to characterize this way: what we know about it, first of all. Secondly, how we know it, and of course, with what confidence we know it. Thirdly, what additional knowledge do we need? What more do we most need to know about the science of climate change? And the fourth big question, which is quite important in the context of policy making, is how and when can we know the additional things that we need to know? We need to make some policy choices now with the knowledge we have. Are there policy choices we could make better with a little more knowledge, or should we simply get on with all of it right away? The questions about climate change policy, of course, are what should we do and when should we do it? And about climate change communication, how can we get better at climate change communication in ways that will make our publics and our policymakers better prepared for the decisions they need to make about what to do and when to do it? So I'll try, at least briefly, to address all of these issues tonight, and I start with the science questions. And I start that by putting before you 5 myths about the science, many of which you will have heard previously. The first such myth is that the Earth stopped warming in the last decade. The proposition that 1998 was the warmest year ever, about which the various institutes which maintain serious global records disagree. It's about whether 98 was the hottest ever or close to it, but I'll come back to that issue. The second one, second myth is if it is warming, something other than human activities is causing it. The third myth, a little warming isn't harmful anyway. What's 2 degrees Celsius among friends, or 3? The fourth myth is that if there is any danger, it's far in the future, that this is a problem for our grandchildren and great-grandchildren rather than a problem now. And the fifth one is the myth that even if mainstream climate science is right and the need for action therefore is real, maybe doing enough to make a difference is impractical or unaffordable. So we just have to sort of hunker down. So I will try to address all of those. The first one, the proposition that it's no longer warming, here's what the thermometers actually say. This is the version of the temperature record produced by the Goddard Institute for Space Studies of NASA. And shown here are the data out through 2011, the last complete year, of course. And you can see that 1998 was, according to the NASA record, one of the 3 warmest years, but not by any means the warmest. And it was also an outlier for its time. And in fact, if you look more closely and try to understand why, the 1998 peak in temperature was way above the trend line due to a very strong El Nino that year. But in fact, the upward trend, when you smooth out the data, has continued virtually unabated. The heating, of course, is not uniform geographically, and I'll come back to that question, but this shows this is not a model, this is not projections, this is a representation of the actual mean global surface temperature averaged over the years 2001 to 2005 versus a baseline taken as the average from 1951 to 1980. These figures are in degrees centigrade, and you see that in the far north and in parts of Antarctica, the warming was 3, sometimes 4 times the average warming for the globe in this period, which was 0.5 degree C. and yet you see the 1.6, 2 degrees in some of these places, particularly the mid-continents, even in the lower latitudes, warm a great deal more than the oceans. Lots of other indicators besides temperature itself have been changing. This shows the annual precipitation trends over the 20th century, 1900 to 2000, where the orange dots are places where the world is getting drier, and the green dots are places where the world is getting wetter. The Earth is getting wetter overall, as one would expect in a warmer world. More water evaporates. What goes up must come down. The increased evaporation means increased rainfall on the average. But because we're fiddling not just with average temperatures and with average rainfall, but with circulation patterns, we're making some areas already prone to drought, even more prone to drought than they were before, and some areas prone to flooding, even more prone to flooding than they were before. Glaciers are retreating all around the world. There are very few exceptions. This is a glacier in the Himalayas. In '68 at the top, you can see this glacier sweeping all across the top, the bottom of the image. In 2007, it's just gone. This was the largest glacier on Mount Everest's northern slopes. Arctic sea ice has been shrinking very dramatically. In these images, the magenta line is the average sea ice extent at the September minimum, which occurs every year in the sea ice extent. From '79 to 2000, that reflects the fact that satellite imagery able to map this accurately only began in 1979. And what you see is 2007 was the previous record, the smallest September minimum since 1979. You see the huge difference between the magenta line and the sea ice cover. And then September 2012 shattered the '79 record by a very large margin. And what is more, the ice is getting thinner as well as getting smaller in extent. And this actually shows both from the early '80s through 2012. So you see the 5-year-old ice is almost gone. And you can think of it this way: the older the ice, the more stable it is. The younger ice is the thinner ice and the ice that is more likely to disappear next year. And so if you look at the volume of the sea ice, the area times the average thickness, it's been declining even faster than the area. Here's the data again through 2012 of what's happening to North American snow cover in June. One of the reasons this is important is land that is covered with snow reflects most of the energy that strikes it. Land that is not covered with snow absorbs a lot more of the energy, and so when the snow-covered area shrinks, the warming accelerates. Another interesting indicator is the fraction of the surface of the Greenland ice sheet that melts over the summer on the surface. This is not melting of the whole thickness. That would truly be a disaster, because unlike floating sea ice, which when it disappears does not change sea level, just as when the ice in your cocktail melts, it doesn't actually change the level of the cocktail because the floating ice is displacing as much water as it will form when it melts. But when we're looking at the land ice sheets, melting is a different matter. Melting enables water to run off. It may lubricate slippage at the bottom of the ice sheet and increase the rate at which glaciers calve into the oceans. That increases sea level. And you see again an interesting thing. The surface melting in recent years peaked in 2007 until 2012, when an estimated 97% of the surface of the Greenland ice sheet melted, even at the highest altitudes, where ordinarily it remains too cold for melting to occur. The mass balance of the Greenland ice sheet. We now have data from a number of different sources. Black refers to something called the mass balance method. Red is the GRACE satellites that make gravimetric measurements to determine how thick the ice sheet is. These are quite consistent, and one sees a stunning pattern of decline. These are figures for how many billions of tons of ice per year the ice sheet is losing. Down at the bottom here, most recently, the Greenland ice sheet is losing about 350 billion tons a year of ice net. Okay. More recently, we've been able to figure out what's happening with the Antarctic ice sheet, which is bigger, covers a much larger area, different things happening in different parts of it, but it too is shrinking, and in fact, the average rate of shrinkage is now approaching that of the Greenland ice sheet, another 300 or 350 billion tons of ice per year, which is showing up as an extra 350 billion tons of seawater and contributing to the rise of sea level. Now, these are some of the latest numbers using a number of different data sets for what is in fact happening to global mean sea level. This shows the trajectory of global mean sea level from 1860 to 2010. The trend obviously is unmistakable no matter which data set you use. And this shows another thing that we're doing to the ocean by virtue of the carbon dioxide that we've been adding to the atmosphere. The carbon dioxide that's added to the atmosphere is not only warming the Earth in its role as a very important greenhouse gas, but a fraction of it, about a third, is dissolving in the surface layer of the ocean and producing a weak acid, carbonic acid, H2CO3. And the pH of the ocean is correspondingly going down. Here you see the trend in actual measurements of atmospheric CO2, the partial pressure of CO2 in seawater in blue, and the pH of seawater going down. And this is a problem, as I will describe in more detail later, that imperils all the organisms in the ocean that use calcium carbonate to form their skeletons and shells. That includes all the coral reefs, the shrimps, a variety of other crustaceans, and more. So all this is very clearly happening, but that doesn't establish what's causing it. It just says a whole series of trends are moving in the direction of a warmer world, a wetter world, a world in which the ocean pH is declining, a world in which ice is melting, sea level is rising. But do we really know that human activities are causing it? Well, this is the account of the fourth assessment of the Intergovernmental Panel on Climate Change, released in 2007, of the relative magnitudes of human versus natural influences on the global radiation balance, measured in watts per square meter average over the surface of the Earth. But you really don't have to worry about what those units mean. This is what climatologists call forcing, and it literally means how hard are you pushing on the climate? How hard are these different factors forcing the climate into a different mode? And you look at the relative numbers, and you see that the warming influence of the anthropogenic, that is the human-caused greenhouse gases, and particles that absorb sunlight and heat the atmosphere, is about 30 times the warming influence of the estimated change in solar input during this period. Some people say, well, it's just changes in the sun that are doing this. That is implausible, both for the reason indicated here, and also because if you look at the temporal pattern of changes in the solar input from the sun, it simply does not match what the Earth's climate has been doing. Now, that in itself doesn't prove that the greenhouse gases were caused by human activities, but the evidence shown here starts strongly to suggest that those greenhouse gas increases were caused by human activities. This shows 10,000 years of atmospheric concentrations of carbon dioxide in the top and of methane, the second most important greenhouse gas affected by human activities, at the bottom. And you look at this curve and you see basically small variations over 10,000 years, and then humans come along and start burning down forests and then burning fossil fuels, and you see this extraordinary spike both in the CO2 and in the methane measurement. But more than that, we know without a doubt that humans are responsible for the CO2 spike, because fossil carbon dioxide has no carbon-14 in it. Carbon-14 is formed in the atmosphere. It has a half-life of roughly 6,000 years. When the plant material that eventually is turned into fossil fuel by processes deep in the earth is sequestered away from the atmosphere, there's no more carbon-14 being produced in it. And over millions of years, given the half-life of only 6,000 years, all the carbon-14 that was there when the plants took it up goes away. When you then burn those fossil fuels, there's no carbon-14, so you're changing the amount of CO2 in the atmosphere with an input that has no C14 in it, and you can actually measure the dilution in the C14 content of the atmosphere that has resulted from our fossil fuel burning. So there's really no question where that CO2 came from. But this is an even more powerful piece of evidence. This is what I like to call the most conspicuous fingerprint of human beings on the pattern of global climate change. It's a little busy as a graphic, but let me tell you what's going on here. This shows basically the period of most of the instrumental record, most of the thermometer record, good enough to define a average temperature of the surface of the Earth. And the top are the forcings. Remember, these are the factors that are pushing on the climate. The greenhouse gases are the red line going steadily up on the right. The black line is black carbon. The blue line dipping downward is the effect of volcanic eruptions, which inject reflecting particles into the stratosphere and temporarily tend to cool the Earth. So all the factors are here. And if you then take that set of forcings and you plug them into a contemporary climate model and run that model, you effectively reproduce the observed temperature trace for the global average surface temperature over this period of 1880 to the year 2000. That's what I call a fingerprint. It's very hard to look at the match on the bottom of these various model runs, the 5-run mean, and then the observations, which are in blue. That's what any scientist would call a rather good fit. And it would be quite extraordinary to get a fit that good if, in fact, these were not the forcings that were causing it. It also works when you start to disaggregate geographically. The geographic pattern of the warming is also as predicted for greenhouse gas-induced change. That is, the observed increases in temperature match the modeled results on every continent. They're different on every continent. The pattern is not uniform. But in every case, the observed pattern cannot be explained unless you include the human contribution from greenhouse gases. So I turn to the question of why worry? You know, the proposition that, okay, climate's changing, humans are doing it, but it's not going to amount to much. Maybe only our great-grandchildren need to worry about it. We need to understand that climate is the envelope within which all other environmental conditions and processes must function. And if you distort that envelope enough, you affect all of those processes. Climate governs, and therefore altering climate will affect the availability of water around the planet, the productivity of farms and forests and fisheries, how much heat and humidity we have to deal with in our cities, governs the formation and dispersion of air pollutants, the geography of disease, what disease organisms and what vectors can thrive, grow, multiply in what environments, governs the damages we have to expect from storms, floods, droughts, and wildfires, governs the property losses to be expected from sea level rise, the expenditures on engineered environments, how much of the Earth's surface are we going to air condition, how many dams and dikes are we going to build to try to protect ourselves from the effects of rising sea level and increased flooding, and the distribution and abundance of species in general, those we love and those we hate. So there's a lot at stake. Are we seeing harm? Well, look at floods and droughts. Chinese data indicate that the East Asia monsoon has been weakening for more than 30 years in a pattern that the Chinese analysts themselves attribute to global climate change. And that has meant less moisture flow in the atmosphere over China from south to north, increased flooding in the south, increased drought in the north, already having serious impact on Chinese agriculture by their own reckoning. This is one of the reasons that Chinese leaders have come to understand that climate change is here and now and that they have to participate in the solution. Wildfires. Wildfires in the American West. This is fires over 1,000 acres on lands in the American West, have gone up in the range of sixfold over the last 40 years. Pest outbreaks. Pine bark beetles. This image is from Colorado, where huge numbers of pine trees have been devastated. They've been weakened by heat and drought, but they're being killed off by pine bark beetles, which have a longer breeding season and more generations in a breeding season, courtesy of warming. Melting permafrost. If you live in the far north and you've built roads and buildings on permafrost, you are experiencing already the consequences of the warming, the melting of the permafrost, the thawing of the permafrost, and the obvious consequences. Coastal erosion. This is in the village of Shishmaresh on the Arctic Ocean. This is not a matter of sea level rise per se. It's a matter of the vanishing sea ice removing the barrier to large storm waves battering the coastal dwellings. In fact, we're seeing all over the world, variously, depending on the part of the world, increases in floods, wildfires, droughts, heat waves, pest outbreaks, coral bleaching events, the power of typhoons and hurricanes, the geographic range of tropical pathogens, and all of these increases are plausibly linked to climate change by theory, by models, and by the observed fingerprints, the patterns in which these changes are occurring. And now we start a forward look. Much worse lies ahead if the planet continues with business as usual. This shows in the middle the target that the EU and ultimately the G20 embraced, trying to hold the global average surface temperature increase to 2 degrees Celsius. You see the actual record in black up to 2000, and you see a set of IPCC scenarios from the previous IPCC assessment going forward and ranging upward to 3 and 4 degrees C by 2100. And it notes along the side that the last time the global average surface temperature was 2 degrees C above the 1900 level was 130,000 years before the present. At that time, sea level was 4 to 6 meters higher than it is today. The last time it was 3 degrees C above the 1900 level was 30 million years ago, and sea level then was 20 to 30 meters higher than today. That doesn't suggest that sea level will get that high as soon as the temperature gets that high. It won't, because the melting and the slippage of the great land ice sheets is a very slow process, but ultimately that's where sea level would be likely to be heading. Now one can run the scenarios out further. These are temperature scenarios out to 2300, according to a recent study commissioned by the World Bank from the Potsdam Institute for Climate Change in Germany. And some of those scenarios go up to well over 4 degrees C by 2100 and up to 8 degrees C and more by 2200. What do we expect to get from that? Well, one thing is hotter summers. This shows the percentage of summers that would be warmer than the current 95th percentile summers under 2 degrees C of global warming. And you see it's quite stunning. A huge percentage of the Earth would be experiencing 90 to 100% of their summers warmer than the top 5% currently. Now that raises a question: why can a small increase in average temperature lead to such a big increase in hot weather? It's a matter of sliding the distribution. The blue shows the previous climate, the new in orange, and you see if you go out to the extreme end of the spectrum, the hot weather, that even though the average temperature may not have increased by much, the fraction of hot weather you get, the fraction of the time that you get hot weather, and indeed record hot weather, goes up dramatically, and that in fact is precisely what we're seeing even at today's level of 0.8 or 0.9 degrees Celsius increase in the global average surface temperature so far. This is of particular interest to people in Europe. This shows both observations in black and one of the Hadley Center models projections, both back projections for the historical period where the match is pretty good, and then forward projections. showing that if you look at the 2003 peak, this was a heat wave in Western Europe, particularly severe in France, southern France and Italy, but also elsewhere, estimated to have killed between 35,000 and 70,000 people, dropped agricultural production in that part of Europe by 35%. And what one sees here is that under a business as usual continuation of greenhouse gas buildup, what was a extreme hot summer in 2003 with those extraordinary consequences becomes not very unusual at all by the 2040s, and it is by the 2060s an unusually cool summer for Western Europe. Declining crop yields are expected, even when one accounts for the CO2 fertilization effect. That is, plants generally varies with the type of plant, but many plants grow better under an enhanced CO2 environment. But even when you take that into account, the effects of temperature stress and water stress, even in the absence of major droughts, drives down the yields of major staple crops. And this shows, as indicated, corn and soybeans in the United States, rice in Asia, wheat in India, corn in Africa, as a function of the global average temperature change. And then you look at droughts. What do we expect in the way of droughts, which were not considered in the previous slide? And all you need to know about this is that while it's a complicated metric of the severity of droughts, what dark brown means is a whole lot worse than what has been experienced in the reference period, 61 to 90. Orange means quite a lot worse. Yellow means pretty bad. And you look at these figures, again, across southern Europe, across the Amazon, southern Africa, southern North America, Australia. It is not something to be happy about. Sea level rise, these are the latest projections from NOAA just out a week ago of where sea level rise could be going. The highest values for 2100 are a 2-meter increase, intermediate high 1.2, intermediate low 0.5. I would say the lowest 0.2 is now wholly implausible. We are not going to get by with that. What do we expect from the continued fall in ocean pH? This one's again kind of busy but kind of interesting. The colors indicate how favorable or unfavorable the water conditions are to the survival of corals. And red means extremely unfavorable, yellow means marginal, light green means adequate, dark green means optimal. We see the historical values in 1870 and 2003 with the corresponding atmospheric concentrations, and one sees that under 2065, we're in a mid-range scenario. You're at 515 parts per million of CO2. Most of the world's oceans have become unfavorable for corals. Interestingly enough, corals are the second greatest reservoir of biodiversity on the planet after the tropical forests. And if you go back to that drought slide and realize how threatened the tropical forests are, you see that we are differentially hammering away at the two largest reservoirs of biodiversity on the planet, the tropical forests and the coral reefs. So is there anything we still need to know? Well, it would be good to have improved understanding of exactly how sensitive the climate is to human and natural forcings. We still have some uncertainty about that, due particularly to lack of understanding of the complete effects of particles and clouds. Sensitivity, of course, means just how much the average temperature increases under a doubling of atmospheric carbon dioxide or its equivalent in other forcings. Improvements in that understanding will improve the capacity of models to make predictions going forward. And getting that improved knowledge will require continuing investments in a bunch of things. Paleoclimatology, that is studying the records of climates in times past by looking at ice cores, fossil pollens, sediments, and so on, tree rings. Basic climate physics, improving and certainly maintaining our constellation of Earth observation satellites, and of course running better climate models on faster computers. We need better regional disaggregation of the predicted changes. We're getting better at that. We're getting better at saying We have pretty good idea what's going to happen in Western Europe or in the southwestern United States, but we'd like to be able to bring that even to a more local level so that people could be provided with the information that they need to take evasive action, adaptive action to the climate changes that no mitigation action can any longer avoid. Does not want to do it. The requirements for getting this additional information are similar to the ones in the first category. We need better understanding of the ecological effects of regional climate changes. It's fine to talk about temperature and precipitation and sea level, but ecosystems are complicated things. My wife is an ecosystem ecologist. She reminds me periodically how complicated ecosystems are, and we don't yet know enough about the ecological effects, although again, we're learning more all the time. But this is going to determine the impacts on oceans, crops, domestic animals, wildlife, pests, pathogens. These are all ecological questions as to what a given set of changes in climate variables will end up doing. And we need that information, again, to shape adaptation strategies. And that means we need to continue making investments in the ecological sciences, and we need major improvements in both the diversity and the density of our ecological monitoring networks, just the measurements we need to make of what's happening out there. And we need better integrated assessments, that is, assessments that combine predictions, mitigation and adaptation options, their character, their capabilities, their costs, and the social dimensions of human response. What determines how people respond to threats of this kind? What are they likely to do, and how will that affect the ultimate damages, the ultimate consequences? And that requires a lot of additional effort as well, both in the methods for these kinds of assessments and the practice of those kinds of assessments, as well as specifics of the mitigation and adaptation options. So let me get to the policy questions. Doesn't want to get to the policy questions. What should we do? There are only three options. Mitigation, things we might do to reduce the pace and the magnitude of the changes that actually occur in climate. Adaptation, the measures you take to reduce the adverse impacts on our well-being that result from the changes that do occur, the changes you don't avoid by mitigation. And the third option is suffering. One can't be too candid about that. Suffering the adverse impacts that we fail to avoid by either mitigation or adaptation and the combination. It's important to understand that we're already doing some of each. We're doing some mitigation. We're reducing greenhouse gas emissions from what they would otherwise have been in many parts of the world. We're already doing some adaptation. We're making adjustments to the changes in climate that are already being experienced, and we're already doing some suffering, as an earlier set of slides showed, and as some of the extreme events that have likely been increased, both in frequency and severity by climate change, have shown. Storm Sandy most recently in the northeastern United States, but the floods, the droughts, the wildfires that have all been going up sharply in their incidence. So what's up for grabs in the policy domain? What we can still influence is the future mix. How much mitigation, how much adaptation, how much suffering? Obviously, our policy goal should be to minimize suffering. And minimizing the amount of suffering can only be achieved if we do a lot of mitigation and a lot of adaptation. These are not alternatives. We don't have the luxury of choosing between doing mitigation and adaptation. We're going to have to do a whole lot of both. Mitigation alone won't work because, as we know, climate change is already occurring, and there's nothing we can do that can stop it in its tracks. It will continue for many decades, even if we were to cut off all greenhouse gas emissions today because of the inertia in the global climate system. Adaptation alone won't work because adaptation gets more difficult, more costly, and less effective the larger are the climate changes to which you're trying to adapt. So what we need is enough mitigation to avoid unmanageable climate change and enough adaptation to manage the climate change that is now unavoidable. A lot of possibilities for adaptation. To preserve my voice and your patience, I won't read this to you. You can read these faster than I can talk. But I will just point out that many of these measures are what we often call win-win measures. They would make sense to do even if we didn't know the climate was changing. we need to be better prepared for the extremes that have occurred all along, even in an unchanging climate. And given that the climate is changing, the benefits are simply all the larger. There are also a lot of mitigation possibilities. Things we certainly can do are reduce emissions of greenhouse gases and soot from the energy sector, reduce deforestation, increase reforestation and afforestation. We can modify agricultural practices to reduce emissions and build up the storage of carbon in the soil. Conceivably, we might do some other things. We might get desperate enough to pay for scrubbing greenhouse gases from the atmosphere technologically. Looks very expensive. We might get desperate enough to do geoengineering to create cooling effects to try to offset at least some of the effects of the greenhouse gases. Geoengineering literally means engineering the earth, and it can vary from very elementary and straightforward and not really dangerous things like making roofs and pavements white instead of dark so that they reflect sunlight rather than absorbing it, to much more far out schemes like injecting reflecting particles into the stratosphere as volcanoes do to try to cancel out some of the warming. That would raise much larger concerns about side effects and costs, but people are starting to look at it because they're thinking society is liable to get desperate enough to try some of these more extreme geoengineering measures going forward, and we need to understand whether there's any potential there, what the side effects are likely to be, what the costs are likely to be, because it would be a tragedy if large-scale geoengineering were undertaken and side effects even worse than the climate problems that motivated it were the result. Some key realities of the mitigation side. Human emissions of carbon dioxide are the biggest part of the problem. Most of that's coming from burning fossil fuels. The rest of it's coming from deforestation and burning in the tropics. The developing countries now exceed the industrialized ones in total CO2 emissions, but not per capita. Nothing we can do can change the global energy system quickly. We've invested about $20 trillion in that system. That is all the power plants, pipelines, drilling rigs, and the normal turnover of that investment is about 40 years. And deforestation is also not easy to change. How much do we need? Well, as I mentioned before, the 2 degrees C increase in global average temperature has been considered by many the most prudent target that might still be within reach. The EU embraced it in 2002, the G8 and G20 in 2009 as a target. If you accept that as the target, it's not hard to figure out that just to have a 50% chance of staying below that target, emissions in the developing countries as a whole need to peak no later than 2015 and decline rapidly after that. Developing country emissions giving them an extra decade to get their act in order because they're starting from a lower level of development and capacity. Their emissions would have to peak no later than 2025 and decline rapidly after that. It's a very busy slide. Let me just tell you the essence of it. This is what economists call a supply curve. This is a supply curve for avoided greenhouse gas emissions. And each block, each bar, tells you both the quantity and the price of avoiding a given amount of greenhouse gas emissions, looking at where we need to be in 2030 to be on basically that 2 degrees C stabilization trajectory. And the stuff you see on the left, which is below the line, are measures that have a negative cost. That means they would make money if you did these things. You would reduce greenhouse gas emissions and you would make money at the same time because the value of the energy you save is greater than what you need to spend to save it. The stuff in the middle that's sort of low bars but above zero are measures of modest cost. And on the far right are very expensive measures in terms of how much it would cost you per ton of carbon dioxide equivalent to avoid these emissions. Now, this tells us something about policy. If you look at the policy needs that correspond to the opportunities at the left-hand side of the curve, This is stuff that people should be doing already because it's already economic, but they're not doing it. Why are they not doing it? Because there are barriers. There are information barriers, there are financing barriers, there are perverse incentive barriers like the famous landlord-tenant barrier, where the tenant has to pay the electricity bills, but the landlord is the one who makes the investments in whether or not to insulate the apartment. So what we need in the way of policies there are policies that remove those barriers, policies that provide financing, that provide information, that knock down perverse incentives. In the middle, I like the fruit tree analogy. This is low-hanging fruit over here on the left, but there's a fence around the tree, so we have to knock the fence down. In the middle, what we need is a price on carbon to motivate reaching higher into the tree. And these are items where a modest price on carbon would suffice to motivate reaching higher into the tree to capture these opportunities, the medium-hanging fruit. On the right, you have the stuff that is so expensive that even a plausible carbon tax or carbon price achieved in another way, such as cap and trade or regulation, would not suffice to capture those opportunities. People still wouldn't be willing to pay for it. So you need research, development, and demonstration to lower that fruit within reach. And those are really the three buckets in which mitigation policy of various kinds can fit. Could we afford to do this? Well, here are a couple rough calculations. If we paid an average of $100 per ton of carbon to avoid half of the current world CO2 emissions, that would cost $500 billion a year. That's real money, but it's less than half it's under 1% of current gross world product. And it doesn't just disappear, it's just a transfer. That is, different folks get the money. It's the folks who are doing the mitigation who get the money in this scenario. If you use that previous supply curve for what we need to do, taking into account the money you save on the left by doing more of these things, the net cost is only about $100 billion a year. That's, of course, a lot of money, but it's a very small amount of money compared to the gross world product. If you use more complicated economic models, they say maybe it'll take 2 to 3% off of gross world product in 2030, 1 to 5% off of gross world product in 2100. Again, that sounds like a lot of money, but if the world economy is managing to grow at even the modest rate of 2% per year, that means people have to wait until 2032 to be as rich as they would have been in 2030 if this money is spent, or they need to wait until, let's say, 2103 to be as rich as they otherwise would have been in 2100. So in those terms, it does not look like an intolerable investment. And I note that the world is currently spending 2.5% of gross world product on defense. The United States now spending over 5% on defense. The United States already spends 2% of its GDP on environmental protection. So the notion that you couldn't afford to spend another percent in order to avoid catastrophic global climate change is kind of a silly notion. Get finally to the communications questions, and I'll be quick here because I've been talking too long. And even if your patience is not entirely gone, my voice nearly is. How can we get better at communication about these issues? I think there are a number of ingredients about climate change communication that are essential. One is to start with the basics. Second is to be clear about terminology. The third is to explain how we know what we know. The fourth is to link it to what people can observe. The fifth is to link the stories to the regions and the communities where the listeners live. And the last is to try to increase people's understanding of how science works and what the sources of authority and credibility in scientific findings actually are. Let's talk about starting with the basics. Here's how I start with the basics. The basics are these. Without energy, there is no economy. Without climate, there is no environment. Without economy and environment, there's no material well-being, no civil society, no personal or national security. And the problem we have is that the world is getting most of the energy its economies need in ways that are imperiling the climate that its environment needs. That is a big dilemma. And when you put it that way, people begin to get how it is that we have a problem. I turn to terminology. I have believed for a long time that the term global warming has set us back. It's a misnomer. That term implies something that's uniform across the planet, that's mainly about temperature, that is gradual and maybe benign. I mean, warming is something that most people don't find inherently horrible. What's actually happening is highly non-uniform. I've already showed that. It's not just about temperature. It's rapid compared to the capacities for adjustment, both in ecosystems and in human economic and social systems. And it's harmful for most places and most times. Some people in some places for some period of time may enjoy some benefits from what's happening. They may be able to swim longer, plant sooner, but for most places, most times, and more as we go forward, it's harmful. So I think a more descriptive term, it would be great if we'd started with this, would have been global climate disruption rather than global warming. More terminology. A lot of folks don't understand the difference between weather and climate. Climate is the patterns of weather, the averages, the extremes, the timings, the spatial distribution, not just of temperature, but of cloudiness, of humidity, of precipitation, of wind. And when you talk about climate change, what you're talking about is disruption of those patterns. Global average surface temperature is just an index of the state of the system. It's like your body temperature is an index of the state of your body system. If your body temperature goes up 2 degrees C, you know you've got a problem. It is telling you something about the state of the system that is disrupted and that needs attention. And that's what a 2 degree C change in global climate would be telling us as well. Lots of things are observables: powerful storms, heat waves, floods, coral bleaching. Anybody who puts their head underwater with a pair of goggles on can see this across the tropics. Linked to the local. I find this a very powerful slide. This slide from the National Academy of Sciences shows the expected percentage increases in median annual area burned by wildfires in the American West for a 1 degree C increase in global average temperature. 1 degree C, and the increases in average annual area burned range from 70-some% to 500%. 1 degree C. We're already at 0.8 or 0.9. Another link to the local you can do is sea level. This is one former doctoral student of mine produced for the area where my wife and I live on Cape Cod when I'm not in Washington. And this shows 1 degree, 3 degrees, 1 meter, 3 meters, 7 meters. 7 meters is how much sea level would go up if you lost the whole Greenland ice sheet. 70 meters, 12 is how much it would go up if you lose the West Antarctic ice sheet and the Greenland ice sheet together. And 70 meters is how much it would go up if you lost all of both. This would presumably take many hundreds, if not thousands of years, but it's nonetheless very striking to folks who live in this region to see what would happen. Last part is about how science works. What people need to understand about science and often don't is, first of all, that uncertainties are two-sided. A lot of folks seem to think uncertainty means that when we learn more, it'll turn out to be better than we feared. Well, in fact, it can also turn out the other way. Yeah, it may not be as bad as the current mainstream forecast suggests, but it could also be worse. And in fact, recent evidence suggests to me, and I think many others in the climate community, that it's more likely to be worse than the current mainstream forecast than it is likely to be better. A second point I want to make is about burden of proof. Climate change skeptics routinely wave in your face a single contrary piece of evidence or analysis. It's often a newly reported one that has not yet been subjected to the scrutiny of the scientific community. And they say, this new result, this new study, this finding I have in my hand proves it's all bunkum. That's not how science works. In all scientific fields, contrary results appear all the time. And when a strong preponderance of evidence points the other way, as is the case in climate change science, isolated apparent contradictions are given due scrutiny, but they're not initially given very much weight because it's far more likely, and all our historical experience shows this is true, it's far more likely that the contradiction will turn out to be explainable as a mistake or otherwise consistent with the preponderance of evidence than it is that the preponderance of evidence will turn out to be wrong. Sometimes the preponderance of evidence turns out to be wrong. These are the scientific revolutions that overturn conventional scientific wisdom, but they don't happen very often, and they happen less the stronger is the body of evidence that supports the mainstream position. All science is contingent. It is possible that persuasive new evidence will come to light that will change the mainstream view, but the greater the consistency and the coherence and the diversity of the existing body of evidence and analysis, the lower the likelihood that the main conclusions derived from it will be overturned. And the consistency and the coherence and the diversity of the evidence and analysis supporting the mainstream view of climate change risk, which is what I've portrayed here, as embodied in reports of the National Academy of Sciences, the Intergovernmental Panel on Climate Change, and other authoritative bodies. This is an immense body of analysis. And I argue that policymakers, on whose decision the preservation and expansion of the public's well-being depends, are gambling against very long odds if they make a bet that the mainstream view of climate change science is wrong. That is the opposite of prudence. Thank you very much.
It's my great pleasure to thank John Holdren for his presentation. Let me also say, not only is it wonderful to have John here, but members of his family here sitting in the front row who I'm sure feel as proud about the lecture we've heard as the rest of us here. But John, the first observation that I would make, I think it would be clear to everybody here that the US President and the US is getting extremely sound and comprehensive advice in the effects of climate change or global climate disruption, as you may offer. You've shown with great clarity the point at which science has reached in demonstrating anthropogenic effects in climate change. I think you've been clear where additional scientific information is needed, where we have more to do, particularly at the regional level. You've been extraordinarily clear about the options in adaptation and mitigation. I think you've demonstrated that we are already adapting and investing in adaptation, and emphasised that pragmatically this is going to be emphasised at the regional scale, probably easier than the global scale. You've also shown us that in principle this is quite affordable. At even quite modest rates of economic growth in the world, the investment that will be required in this mitigation and adaptation is affordable. I guess, John, thank you for being so clear. What the world really needs is not only John, more people like John, banging away with messages of this great clarity to policymakers, probably for several more years and possibly decades to come. It's been a great pleasure to have you here. Lecture of tremendous clarity. The voice held up better than the little clicking device here, but you know, congratulations to both parties. Again, a warm welcome to the family. John, can I ask the audience to thank you once again for a splendid lecture? Thank you.